We are almost done. For millions of years, humans have asked the question, is OVMF too slow for serverless confidential computing? Before I answer that question once and for all, I want to say thank you to some people at AMD, Tom and David and Mike, for giving me some big pointers on this, and also to my colleague Chris Porter, who helped me through a lot of the work here, and I would have lost my mind without him. So you'll see why, probably. I want to give a few disclaimers. First of all, I should apologize for having a somewhat dramatic title. I'm not actually going to be making any really big claims in this talk. I also want to say that you might detect some undertones of frustration with OVMF in this presentation, but I actually like OVMF. I think it's cool, and none of this is intended as a slight at that project. Also, I wanted to point out that this is not really a talk about serverless. So if you don't like serverless computing or you don't know what it is, don't worry. I don't really like it either. This is really just a talk about booting VMs and trying to do it kind of quickly. And the last thing is that this talk has some audience participation, and it's mandatory. But it'll be fun. So just be prepared. Try and pay a little bit of attention so when we get there. OK, so why am I here? Partly because of these two papers. There's other contributing factors in my life too, but mainly it's these two papers. One of them is this from Carlos Segarra, a person I know, who was looking at doing serverless confidential computing on top of this confidential containers project that I've been involved with. This other presentation is from Ben Holmes, and this was actually supervised by Dan Williams, not the Dan Williams that you guys may have bumped into at LPC this year, but it's the other Dan Williams who you actually may have bumped into at LPC last year. Either way, both of these guys were looking at the performance of confidential computing in serverless. This is kind of a tough nut to crack. There are a lot of issues with serverless. First of all, in serverless computing, you often do some sort of warm start. You often try and not boot things as many times as you might otherwise. And doing this with confidential computing is kind of annoying. There might be attestations in the way, for instance, you might have a guest that's already sort of linked to one client. Cold starts are also slower and more complex, unfortunately. That's, again, what I'm really going to be talking about in this talk. But I do want to also mention that usually starting a lot of guests at once is slow. And this is where I have to say that we're into the AMD specific territory in this talk. Both of these papers identify this trend, which you probably already know about, which is that starting a bunch of guests tends to scale linearly. This is because pre-encrypting the memory is serialized at the PSP. This is really not great for serverless. And in fact, these two graphs might answer the title slide already, but we're going to keep going and talk a lot about cold starts. So both of these papers evaluate cold starts. I should point out, though, that neither one of these papers is really about evaluating OVMF. Both of these papers are doing other things. Both of them care about measurement. You might know a little bit about like this bootstrapping thing, like this SEV hashes thing that's going on. And both of these papers actually point to this a little bit. You can see the OVMF measure verify stage over here and the green thing over there. That's the verification of the hashes. But in my talk, I'm not talking about measurement. I'm really just going to be talking about boot time, and I'm not going to be talking about the AMD SEV firmware package either. It's worth noting that these two papers have different configurations for their guests. They're using different kernels. This one is using SEV SNP. This one is just using SEV or SEV-ES. So there's a lot of stuff that's different here, and in some ways that's not too rigorous. But I also think it's fair to ask this question kind of generally. Like if a user shows up, or if someone shows up and uses this thing with whatever configuration they might find, should they expect it to be a good experience or a not so good experience? And from these two graphs, you might say it's not going to be that great, because both of these papers identified some interesting delays that you might not expect. Look at this time, 6 seconds to boot a guest. Keep in mind these graphs, some of them include the kernel booting, which my graphs do not. Some of these also involve what goes on before you start the guest, which my graphs that you'll see shortly also don't. So Ben found some overhead in the BDS phase, the boot device selection phase. That's the crosshatch guy over there. And Carlos found some overhead in the Dixie phase. Okay, now for the big reveal as to what I ran into. So first of all, I want to point out that I did some of this testing on an oldish kernel, but I also have results on the new kernel, the upstream one, coming soon. It's going to be sort of interesting to compare these, because for one thing, this version of the kernel has huge page support, and the one that we're going to be looking at later does not. So think to yourselves, how is that going to look? But let's cut to the chase. For my results, SEV, no SEV is the top over there. Then we have SEV and SEV-ES, and all of those look fine. Let's face it, that's okay. But when we start getting to SEV, SNP, that's not great. So we'll talk about what happened here. First of all, though, if we do a quick comparison, Ben also had a problem in the BDS phase, right? So maybe I'm running into the similar thing that he's running into. Nobody had this issue in the sec phase, and spoiler alert, I don't know what causes that. Yeah, in general, some alignment. Also, yeah, Carlos's slowdown in the DXE phase, I could not replicate that. I suspect it's attached to some particular device. But yeah, last thing to mention here is that his configuration and mine are somewhat similar because we both were basing this somewhat off of CATA/confidential containers. So maybe he had some extra device that I didn't, I'm not sure. But don't worry, we will get into what is slowing down the BDS phase. And I think I have some answers. But before we get there, I want to talk a little bit about methodology. And this can double as advice to anybody who finds themselves debugging OVMF. There's a couple of different things you can do. Some of them work okay. So OVMF has support for a debugger, for instance. You can connect GDB to it, but not if you're using confidential computing, usually, at least not with a lot of messing around. So I didn't do that. OVMF ships with some EFI profiling stuff built into it, but the granularity was not right for my project, so I didn't use that. Printing, hey man, printing stuff, everybody's favorite method of debugging, that's what I did. In particular, I printed out the performance counter all over the place. There's a few things you need to be careful with here because printing does create more VM exits. So I introduced a new debug level in OVMF so it would only print out my profiling things. And then I also checked how many VM exits I was getting to make sure it wasn't going through the roof. The performance counter in OVMF can be useful, but there are places you can't use it. In those places, you might be better off using RDTSCP, although that can be a little bit more difficult to work with. And this is one of the reasons why I was not able to get to the bottom of what's going on in the sec phase. That, and I ran out of time. Maybe next year, we can have this conference like a week later, and then I have a little bit more to show you. But anyway, there's also KVM tracing. So if you know what exits you're looking for, you can see if there are more of them. This wasn't very useful for me because I really didn't know what I was looking for. And it turns out that the stuff we see wouldn't have actually caused more exits necessarily. So, interesting. There's also the EFI shell. This is a really good thing to know about. If you're working with OVMF, you can boot into this EFI shell and check out some stuff that you really are going to have a hard time finding anywhere else. And we'll look at a little bit of that later. Fuzzing, some people have done this to OVMF. I didn't do it, but based on some things I found, this might be a good thing to continue doing, especially on certain interfaces. The final thing you can do is read the spec. The EFI spec is a mere 2,000 pages, and it's really exciting. But actually, the tip I'd give you is that the driver writer's guide provided by EDK2 is actually really good. Unfortunately, it doesn't have anything to do with virtualization, but it gives you a pretty good overview of what OVMF is doing. Okay, so the first thing you're going to think about when you're talking about overhead for SEV SNP is that it's got to have something to do with memory p-validate, right? Spoiler alert, nope. So there's a couple places where this happens in the guest. I won't go through all of this exactly, but there's basically 5 places. You'd think it'd be more, but not that many places in OVF where it happens, and none of them are part of this graph. By the way, I know you might be thinking, wait a second, you have the slowdown in sec, and there is p-validating going on in sec. I checked, it is not what is causing that blue, really big blue bar over there. So p-validate is not the culprit. Let's break this graph down. By the way, I adjusted the scale of the graph. I know it was so annoying that it ran off, but this is equivalent. But this is showing the phases a little bit differently. So that was all the standard OVMF phases on the previous slide. And this shows us the BDS phase. So the blue is everything before the boot device selection phase, which you might not really expect to be slow, but turns out it is. And these are different parts of the boot device selection phase. And this maps to these parts of the source. So these are relatively small functions that are causing pretty big problems. And I have no idea if you can read this from where you are, but they have something to do. This one is EFI boot manager connect console variable. Interesting, we call that twice. And over here, platform manager, boot manager before console. That function does a lot of things. Neither one of these things off the top of my head I expected to be particularly slow, and I was a little bit stumped for a while. So I thought maybe I should just try to systematically remove some devices and see if I can get the results to change, and they do. So here's where the audience participation comes into play. One of these devices made the graph go from the left, which is what we were just looking at, to the right. Kicking out one of these made OVMF boot significantly quicker. Do you think it was A, this scary network device, B, this seemingly innocuous NUMA command, oh gosh, C, SCSI, oh man, we've got some heavy hitters here, or is it D, VirtIO RNG included as a joke, or is it? Okay, who's for A? You have to vote, remember? Who's for B? Okay, Numa, Okay, who's for C? Anybody for D? Okay. Yeah, the answer is D. So, first of all, I gotta tell you guys, you should not be using virtio-RNG in a confidential guest. And one takeaway from this presentation is that we need to update CATA/confidential containers to not do this. And we should do that ASAP, I would say. But you might be wondering, why are we even calling virtio-RNG? How is this even involved? And it comes down to, well, in particular, what does it have to do with connecting consoles, right? Well, if you want to know all the details, you can look at section 3.15.3 of the driver writer's guide. It tells you about how OVMF goes through and connects the consoles. The thing to keep in mind, really, the Cliff Notes version is that OVMF is not very enlightened, and it knows something about the device tree, but it doesn't really know what any of these devices are, and it basically is going to end up trying to bind most of the devices that it has to most of the drivers that it has. So even if you don't even have a virtio-RNG device, that virtio-RNG driver binding code is going to be called a lot. And when you go to connect the console, what you're doing is you're looking at this console variable, and it's going to be a device path, which you're basically going to iteratively parse, and you're going to end up calling the devices, a ton of device drivers, a lot. Okay, but why is virtio-RNG actually slow? And the answer here is that it isn't. So if you actually profile the virtio-RNG code, the device binding code, you'll find that it's not slow. But when it is enabled, something else is slow. This is not great. But here's where the console came in. So again, I don't know if you can read this, but on the left, we have, this is the EFI console. It can give you a list of all the devices that you have. It can also tell you about the device tree. It's great. It's useful. It can tell you about your EFI variables too. We'll look at that a little bit. But yeah, so on the left, we have without virtio-RNG enabled. And on the right, we have with virtio-RNG enabled. And I don't know if you can read this, but right here, there's an iPixie device. So when we enable virtio-RNG, we get iPixie. That's interesting. Okay. I went through iPixie and profiled that. iPixie is not slow either. Anybody hazard a guess at what these things have in common, though? Virtio-RNG and iPixie? The answer is SCSI. So it turns out the multiple choice question was kind of a trick in some ways, because that SCSI option does have something to do with it as well. For some reason, this is slightly odd dependency management, but for some reason, when you enable virtio-RNG, you get SCSI, and you also get iPixie. And most likely, SCSI depends on virtio-RNG, and iPixie depends on SCSI, or something like that. But this is a little strange. So this is one of these OVMF quirks. Okay, so why is SCSI slow? And it is. You can go through and profile it, and you'll see, yes, finally, all of these cycles I've been searching for, they're eaten up right here. And in fact, they're eaten up in that block of code, which on the surface doesn't look too bad. Why is this slow? Well, because it is setting a lot of EFI variables. It's modifying the NV data. And that is what is slow. Finally, we get to the root cause, sort of. Now, why was that slow on SNP, but not on SEV? Well, maybe it's actually because of a bug where SEV-ES fails to use the QEMU flash driver. This is where we start to enter a lot of kind of strange territory, though. Okay, but before we go any further, I want to talk about the new kernel. I think that's what's on the next slide. We'll see. Yes. So on the new kernel, this problem was solved, right? So hopefully I didn't just waste everybody's time, but I do think that there's a couple of good things to talk about here. Why was it solved? I'm not entirely sure, but I think it is possible that it's because we no longer have read-only mem slots for these SVMs, where we used to, and that when we were using the NV data in the past, it would have been assigned to a read-only mem slot, and then when you try writing to it, you have to do some messing around, essentially. That's my theory. But yeah, there's, I think, some important things to keep in mind here. First of all, this new graph tells us something about huge pages support, right? So the sec phase, which is in this magenta color, is slower. But it's actually interesting that it's much less significant than this overhead of setting the EFI variables was, which is not what I had expected at all. Now, this is not to say that huge page support is not important, because you're going to use it a lot more throughout the rest of the boot. This is only OVMF, which is really not dealing with that much memory. But you almost certainly want this for the kernel. It's going to be key. But one thing to keep in mind is be careful. This is a hard space to optimize in, and there might be things that you wouldn't really expect to slow down the guest a lot that could be very significant, and EFI variables is one of those things. There also is some ongoing discussion about the flash stuff, right? So I saw, for instance, there was one of the commits in the SNP series was about using pflash, was about using the new BIOS flag with pflash, right? And this was ultimately dropped. I think because people thought it was just kind of weird to use BIOS and pflash both, which, let's face it, it is. But there's still some discussion here about what are we actually supposed to be doing with these QEMU flash things. Some people have talked about like these should be provided by the SVSM, or there's sort of a fundamental issue here. You know, in SEV we don't measure these things, right? If you specify like a flash 1 drive for like legacy SEV, we don't measure that, and that's interesting. I think the idea is that you don't want this thing that's volatile to change your measurement and screw it up, but it's possible these things are security sensitive. So there's a little bit of a puzzle there that I think we've never exactly solved. Just for reference, these are this is the NV data. So again, this is from the EFI console. You can print out the NV data. And this is what I have for my guest. And actually, none of these things are security sensitive at all. So, you know, maybe who cares? I know there's something called key 1 here and key 0, but those keys are like the hotkeys you use to get into the BIOS. They're not like secret keys, although secure boot keys can be stored here, so you need to think about this. From my guest, I think the most malicious thing that you could do is modify this to change the system language to check. I think that qualifies as an attack, but somewhat easy to undo that. There are some things I think we do need to take a much closer look at, though, with QEMU Flash, though. Yeah, someone who knows a lot more about Flash than me, I think, should really go through this QEMU Flash driver, because I think there are some gremlins here. And one thing that's notable is that when we are using the new upstream kernel patches with SEV, SNP, we still hit the QEMU Flash driver, even when we're using the BIOS flag. I'm not sure we really should be, and it seems like we're still trying to write to Flash. I also found cases where writing to this Flash would end up with some corrupted variables, because I don't know if you can see this, but at the end of writing to Flash, we write this read array command to set the Flash back to being like, that's like, hey, I'm done writing, essentially. You want to give Paolo a mic? Oh, no. What? Did my computer go to sleep?
So I'm not sure I remember correctly, but I think what happens is that with SMP, there's no memory, read-only memory, so it becomes pure MMIO. So it becomes slower to read, but you can still write to it, because writes were MMIO also before. Now the reads and writes are both MMIO. The difference is that with the read-only memory support, you can execute in addition to reading, while with SMP, there's no memory slot at all, so you cannot execute from it. So you will hit it, and you will also hit it more slower, because you will hit it for reads and not just for writes.
Yeah, interesting.
So you'd better not use Flash at all, and in this case, you just don't have the memory.
Yeah. OVMF is
I'm not 100% sure, but it's plausible at least.
Yes. There's a lot of different cases here for SEV with one Flash device, with two Flash devices with it read-only, with it not. There's a lot of cases here. Some of them I don't think are behaving quite correctly. For instance, there are times where there is no Flash and it's backed by memory, and we're still calling this code, and we're writing this read array command into memory, which corrupts some of the variables, which I don't think we want to be doing that. In fact, I'm not sure that we should be calling the QEMU Flash driver at all. And for SEV-ES, we don't use it, but I think the reason why we don't use it is actually because there's some weird bug in the initialization phase where the header, the firmware volume header that we expect to find at the certain memory offset gets trampled somewhere during boot, during SEV. So yeah, it seems like we're doing it correctly for SEV, but I think it may actually be a bug that's happening. For SNP, I'm not sure we're doing it correctly. So anyway, moral of the story is, like I said, someone who's a little bit better versed in Flash might want to take a look at this QEMU Flash driver and just make sure. And there is also still some discussion going on about what are we even doing about Flash in the first place. You know, is the SVSM going to handle this eventually? Do we want these things to be measurable? There's a lot going on here. Okay. Conclusion. So, oh right, I had this big bold question that I was going to answer in this thing. Well, the answer, I hate to do this to you guys, is yes and no. I think honestly that the big slowdowns that we saw in those papers are not necessarily inherent issues, and I think I think we can get around those things. And if we're looking at like 6 seconds to boot like an SNP guest, that's too long, and that's probably a bug, and OVMF is not going to result in that. That said, in serverless, every single byte of your firmware does count. We talked about the overhead of the pre-encryption phase and how that's serialized. So, you know, there is ammunition for saying that you would want to use something else. To me, I think the biggest overhead, by far the biggest overhead when using OVMF is actually none of this stuff. It's the overhead of using OVMF as a developer and trying to put optimizations in it and trying to understand all of the different cases, because that is pretty slow. And OVMF is inherently a complex program. It's doing something that is complicated, but there is also other firmware that maybe cuts some things out. So something to think about. There are also a few concrete things to fix. So we got to remove virtualization from Kata. That should not be there. There's also a few configurations that QEMU will let you use that I'm not sure are really supported. Like with the new kernel, you can use the BIOS flag with SEV and SVES, and everything kind of seems to work. But if you do it wrong, that's one way you can get this weird sort of writing into writing these commands into memory, thinking that it's flash thing, which I don't think we really want. It also might be good to try and document this a little bit better, just to make people slightly more aware of like what you're supposed to be doing. Here again, somebody else should take a quick look at this QEMU flash driver and just see if it's sane. And then also, I would like to get to the bottom of this sec overhead at some point. And if anybody has any suggestions about what they think that might be, please let me know. I think this is the last slide. I forgot to put a question slide, but you may now ask any questions that you have.
So, really good work. I agree with your statements, like OVMF isn't inherently slow. It is surprisingly complex, and a phase you shouldn't be executing in serverless. Like the whole point of serverless systems these days, at least, like now that we have done them for the last decade, is to move to a snapshot model. So what we need to do here is we need to figure out how we can create a sensible SVSM or TTX-enabled snapshot restore mechanism, right? So, and that may actually be finally a valid use case for SVSMs, where we get an SVSM inside of our VM that then is able to on demand go and page my payload in. We just need to make sure that the hypervisor state, device state is also synced. The other piece, going back to the very, very early part of your presentation, would have been good to sync up beforehand. I did patch this a few years ago to provide an in-memory timestamp boot lock for OVMF, for EDK2. So you can basically, you get a, effectively in Linux, you then get in sys firmware boot lock, you get boot locks for every component that ran before Linux, and that includes EDK2. And so you just enable a debug build of EDK2, you tell it dump into this boot lock that's in memory, and then you get a fully timestamp boot lock that doesn't impact your boot times, but allows you to very fine-grain just do normal printf development, which is what we're all used to and love, right?
Yeah, that sounds like great work. And I agree, by the way, the SVSM Coconut is a lot smaller than OVMF, and something, I don't know if you'd call this like a warm start or whatever, but doing some kind of snapshotting thing like this is probably a good approach.
So was this slowdown just because of the Virtio RNG device, or do you add some other random device and it still shows up? Is it the device thing itself, or this specific device?
Yeah, so to be totally clear, on the older kernel, which is not upstream, but on the older kernel, what the slowdown, the root cause was setting the NV data. So it's setting EFI variables. And anywhere you would do that, there would be some slowdown. Like you noticed that this presentation was mainly investigating the second part of the BDS phase. Didn't talk about the first part, but yeah, it turns out we set some other EFI variables in that section, right? So the place I ran into it was because SCSI sets a bunch of EFI variables. I think there's one called like number of attempts that it sets. And yeah, that was slow. And because of some OVMF weirdness, that SCSI code was being called when Virtio RNG was there, but not when it wasn't.
By any chance, do you know what the Virtio RNG backend was? If it was trying to initialize and Virtio RNG, I don't remember I wrote Virtio RNG, but I don't remember the code right now on what it does on probe. But if the backend on the host reads from dev random, maybe the host doesn't have enough entropy and it has to wait. If you switch it to dev urandom, all of this should be faster. So
yeah, I tried both of those things. No difference.
All right.
And like I said, benchmarking I benchmarked the actual like VirtIRNG code for the probing and the binding, and it's not slow. So good job with your work.
Yeah. So regarding there's some logic there where I think for SEV-ES, if it was a read-only mem slot and then it did its normal probe to see if it was a flash device or normal memory that it could write to, it would basically shortcut it so that it would end up using MMIO instead, because those probes would try to write to the read-only mem slot, and that would cause VC, and then you get into an infinite loop. So there's some code there that says if I'm SEV-ES, just skip all these checks and just assume I'm a flash device. And then somewhere else in the code, when it actually does the writes, it uses MMIO VMX, GHCB calls to do the writes. But now, pretty late in the development cycle, on the QEMU side, on the kernel side, we disallowed the use of read-only mem slots, and that was one of the reasons that on the QEMU side you now use -BIOS, because when you take that approach, it doesn't map it as a read-only mem slot. So I'm wondering now if you could just write to it like normal memory, and that would just make everything speed up, and you just treat it like normal memory. The flash would still be ephemeral and it'd go away, but that's sort of kind of by design right now. Yeah.
Yes, I think we should be treating this as normal memory. The one thing to keep in mind is that OVMF also has a fallback emulated NVData driver, and QEMU Flash, it's going to have this special exit for the VMG exit thing to do the MMIO. I don't think we should really be getting into that code path at all. I would be fine with just falling back and using the built-in OVMF fallback thing. Yeah, that's what that would result in. Yes.
And maybe when we do the -BIOS, instead of doing the full OVMF.FD, you just do OVMF code.FD, and then it'll just use RAM completely, I think, for the variables.
The ephemeral build of OVMF is what we do in Fedora and RHEL for SEV and SVS right now, because, as you say, the NV bit is not measured, so you don't want it there at all.
Yep.
From 0% to 100%, how much is the confidential warm start a migration problem? Like something that you basically need to sort out how to load memory as if it was a migration, and then, however, still get the same attestation report as if it was a cold start.
Yeah, so I guess the question is, how similar is the warm start to migration? It depends on exactly what we mean by warm start. I think maybe snapshot is a better term, which is what Alex mentioned. And yeah, snapshotting in some ways is pretty similar to migration. There are also potentially much simpler ways to do something for serverless where you just start a guest ahead of time. Here's where you need to be a little careful with the attestation, because that will be sort of scoped to the boot time. But maybe if you know that one client is going to be booting a bunch of functions or whatever, and then you boot up a bunch of guests for them ahead of time, you can do a type of warm start, which is way simpler than like doing a snapshot. Yet, how similar is snapshotting to migration? The thing that I actually think it's maybe more similar to is some of the stuff we were talking about from like booting from the SVSM earlier, or like booting even Alex's talk to some degree about booting like a different kind of guest. I think is somewhat similar. Because
the snapshot also has the advantage that the thing that actually does the decryption can be very small. You can put the actual data unencrypted, like encrypted but in shared memory, encrypted with a kind of transport key. And this way you can then check that it's actually the firmware that you want, but you only have to pass to the ASP a small decrypting trampoline, and therefore you also kind of fix the the launch update serialization problem.
Yeah, I think we're out of time here, but I would just say as the final thought that I think stack collapse, like what you're talking about, is very good. And ideally, if you care about serverless, you shouldn't really be using OVMF at all. You should be taking as many shortcuts as possible. And I think that's something we should be trying to look into as much as possible. Thanks, everybody.